Okay, well, let's go ahead and get this research exchange started. My name is Yvette Subramanian. I'm here with CITRIS, and I'd like to welcome Ethan Miller from UC Santa Cruz. He's going to speak to us today. First, I'd like to thank Infineon for sponsoring our lunches that you're enjoying right now. Hello to our web viewers, of course. We have the other CITRIS campuses watching, the UC Merced, Davis, and Santa Cruz, as well as basically anybody who wants to. A couple quick announcements. Everyone is invited to our holiday gala, which is going to be Friday, December 12th. There are flyers in the back. It'll be out in the lobby in Hearst Mining. It's a lot of fun from 4 to 6 p.m. And we have another distinguished speaker on December 5th. The Danish ambassador will be here to speak about the EU as an emerging power, and there are flyers in the back as well. And with those announcements out the way, I'd like to just introduce Ethan Miller. He is professor in the Computer Science Department at UC Santa Cruz, where he is the Associate Director of the Storage Systems Research Center. He received his PhD from Berkeley in 1995, where he was a member of the RAID project, and he's currently interested in long-time archival storage systems, which he's going to talk to us about today. So please join me in welcoming Professor Miller.
Oh, thanks, Yvette. Actually, normally when I give this talk, I have a nice slide up here which shows how nice Santa Cruz is, beach and everything. It doesn't work as well in Berkeley because you guys have a pretty good view here as well. But when you give this talk someplace in the middle of the country, they look at it and go, "Wow, that's pretty good." So it's in some sense also a recruiting tool. So if you want to actually go join the faculty at Santa Cruz, know people who want to work on a PhD at Santa Cruz, yeah, this beach is about 2 or 3 miles from campus. Okay, so what I'm going to talk about today is archival storage. And before going into what we've done about making archival storage work better, I want to first motivate why we even care about archival storage in the first place. And the primary reason that we care about it is that as things go on, we are storing more and more data digitally only. So show of hands, how many of you guys have digital cameras here? That would be just about everybody. How many of you have a photo album of prints you've made from your digital camera? Okay, take a look around and notice that a lot of people have digital cameras, want to save the pictures, but only a half dozen people actually bother to print out even a few of them and save those. So what that means is that all the images you've captured on your digital camera exist digitally, but don't exist analog. Right? I know looking at photos my grandparents took 60 years ago, they're all printed. I can read them. Well, for those of you who have digital ones, I sure hope you make backups and have other ways of keeping them around, because otherwise they'll disappear. But it's not just personal data. There's also financial records, medical records, right? All this stuff is digital. And the problem with digital is that digital has this nasty tendency to disappear when the underlying storage gets corrupted and when it goes away and when it's not maintained properly. And this is a very, very big problem. It's one that a lot of companies are starting to think about, gee, this might be a problem. Okay? People like Yahoo, for example, and Google, who store all of your photos, who store all of your videos. Those things are stored digitally, and they've got to worry about storing them not just for the near future, but for the long-term future. Right, so again, show of hands, how many of you guys store your photos online using a site like Flickr or oPhoto, something like that? Show of hands. Okay, how many of you expect that those photos will be there in 20 years? Let's see, so you have to hope that Yahoo's around in 20 years, which may not be the case. 20 days, actually, at this point may be a little bit iffy. But certainly Yahoo and other people have actually shut down photo sites. I don't know if people realize that. Yahoo Pictures was shut down. They told you, yeah, just go ahead and use Flickr instead. So this is a real concern. How do you actually store all this information and pass it on to your descendants? Now, the first thing I want to point out to you about archival storage is this is storage that you don't use very much. Okay, so Berkeley has a really big library system. In fact, I think it's not the largest library in the country, but it's one of them, right? What fraction of those books do you think are taken out on a regular basis? 90%? You got to be kidding me. We're talking about way under 1%. They have really, really big buildings to house all those other books that nobody really looks at very often. But if anyone makes those books go away, you're going to be really, really upset about it. So the first thing about archival storage is that you've got hot data and cold data. Data that the photos you took in the last 3 weeks, you're still probably passing around to your friends, photos of the party, photos of the last football game. You're passing those around to your friends. Those get a lot of usage. The exact same photos analogous to that from 3 years ago, the photos from the football game 3 years ago, probably not being used by a lot of people, but you want to keep them around anyway. Okay? Now, this is really part of the long tail problem. So how many people here have heard the term long tail before? Hopefully most of you. Archival data is the long tail. What that means is that we've got gigantic amounts of information being stored. If we only knew what we were going to use later, we could get rid of most of it. Except we don't. Given the recent election, how many of you 10 years ago would have kept pictures of Barack Obama? 10 years ago, not 2 years ago when he gave, not when he gave his last speech at the convention 4 years ago, but 10 years ago. Guy's going to be president of the United States, right? Good luck predicting now who's going to be president of the United States in 20 years. But the photos you take of that person doing really goofy things in college, those will be worth an awful lot of money in 20 years. So we can't predict what we're going to need, but we know that we're going to need some of it. And since we don't know what it is, we keep all of it. It's cheaper than trying to figure it out. Now, it's not just a matter of keeping all of it. We also have to make sure we don't lose it, because if you say, I got this great picture of Barack Obama shaking hands with whoever it is, and that picture is corrupted, you're very upset. We also have to be able to find it, because yes, there are lots of good pictures of famous people doing interesting stuff 20 years ago, but there are also a lot of pictures of your cat playing with a ball of yarn, and you probably don't care so much about those. So we've got to index it to that we have. So we've got to preserve it. We've got to make sure that it lasts, not just preserve it, but manage the long-term storage, and also index it, make sure we can find it. So a lot of people confuse archival storage and backup, because after all, these days anyway, they both involve writing lots and lots of data to tape. We're going to fix the tape problem, but we'll get to that in a minute. But archival storage is not backup. The goal of backup is in case your primary storage fails. In other words, in case the data that you've put on your hard drive goes away, that's why you have backup. The lifetime of a backup is until you make the next backup. And you never touch a backup unless something bad happens. Oops, I deleted a file. Oops, my hard drive completely crashed. By the way, just as a public service announcement, how many of you guys make regular backups of your laptop? The rest of you, shame on you. Because I can pretty much guarantee, just show of hands, how many of you have ever had a laptop hard drive fail? All right, those of you who aren't making backups, look around. Okay, so keep backups. But the point is that backups are not archival storage. Right? The backup is there so that when your laptop drive fails, not if, but when, you have something to go back to and get your data back. But you will never read your backup unless there is a failure of some kind. Archival storage is different. Archival storage is the only copy of a lot of data. That 5-year-old picture you don't have on your laptop necessarily. You don't have it on really fast storage because it's too expensive to keep it there. That is the only copy you have. You darn well better not lose it. If you lose a backup, what happens? You just make another backup, assuming your hard drive hasn't failed at this point. No problem. You lose archival data, you are out of luck. Okay, so here's the difference that you have to. Here are the differences between the two that we have to be aware of. First of all, archival storage is write once and read, yeah, maybe, maybe not. Maybe for some really, really low value of maybe. Backup storage is write once and hope to God you never have to read it. You will, but you hope you don't. Archival storage is also random access. When I'm looking for things in that long tail, it's random what I'm looking for. I have no way of organizing it very well to predict what I'm going to use. Backup, though, if your hard drive fails, what do? You read the entire backup onto your new hard drive. Well, that's not random anymore. That's sequential. Tape's good for that. The lifetime, similarly, is much longer for archival storage, essentially forever. Backup, look, I mean, I have backups from 3 computers ago that I am never going to use again because I don't need them. The backup has to live as long as it takes to make another full backup. Now, for backups, you have to have very high bandwidth because you're making extra copies a lot more often. Archival storage is pretty moderate. And you really don't have to index your backup. It is very rare that somebody, if you have a good file system, goes to backup to find one file. They go to get all of them. Okay? So now what I want to do is compare what backup needs to what you can probably buy in the market today from any one of a dozen vendors. Okay, because that's really what we're looking at. Traditional enterprise storage has a variable workload. Some people want to do lots of reads, some want to do lots of writes, but the point is there's reads and writes in there. Archival storage, as I said, is write once and maybe read it. Traditional enterprise storage is also very heavily driven by performance. It's got to be fast. Okay, fast is the biggest criterion for buying what companies want to buy. They don't care that much about whether or not it's reliable, as we'll see over here. Short-term reliability they care about. In other words, they want to make sure that it's not down every 3 weeks. But if you tell them this one will last for 5 years, this one will last for 5,000, their reaction is, well, but 5 years is past my planning cycle, so that's good enough for me. I'll just replace it in 5 years. Archival storage, you can't do that. Another thing is cost. people are willing to pay an awful lot of money for enterprise storage. I mean, you can buy a hard drive these days for on the order of, I think it's what, 5 cents a gig now or something like that. I mean, or at most 10 cents a gig. It is really, really cheap. But you can't buy enterprise storage for that because they got to do all this stuff to make it fast. They've got to do all this other stuff to make it accessible. Now, for archival storage, remember, this is stuff you might not ever need again. Your key word here is as cheap as you can possibly make it, and then make it even cheaper than that. So there's also scalability. For enterprise storage, you want to make it a little bit bigger. But if you're building an archive that's going to last for 50 years, well, you've got a lot of problems. You've got to worry about what will happen when this vendor goes out of business. What will happen when technology changes, right? Think about a storage system you would have built in 1975. Your big technology vendor might have been AT&T, which probably would have been a bad choice. If you chose IBM, it was a good deal, except for the mid-90s. But you might have chosen AT&T or Unisys. Apparently Unisys just got kicked out of the S&P 500. Right? They were big in 1975, not so big anymore. You would have completely missed out on companies that have come up since then. The point is that archival storage has to scale in a lot of dimensions: capacity, time, technology, what happens when we go to flash memory, as opposed to just, gee, in 5 years I roll an old one out and roll a new one in. It's a big difference. So, as I said before, we want to preserve archival data for a really long time. Now, we know that we're not going to be able to get a single device that's going to last for hundreds of years. We can't build one. We'd like to, but it doesn't exist right now, with the exception of maybe stainless steel discs that use ion beam etching, and yeah, it's not such a good technology for random access and a lot of other things. But things like hard drives, flash memory, tape, they don't last for very long. So we're going to build something that's going to evolve over time, okay? We're going to make sure that we monitor data to make sure it hasn't changed. Again, modern enterprise storage systems do this as well, but they don't do quite enough to make sure that changes don't happen. Now, power is a really big concern, and obviously everyone cares about power now, right? Power is the new buzzword, but for archival storage it's especially important because you've got to make sure that you don't use that much power. Standard disk drive uses about 10 watts. So that means that if you leave it running the whole time, it's on the order of 10 watts a terabyte. Doesn't sound so bad, right? Except that when you consider that somebody like Yahoo has literally petabytes of data, 10 times thousands is now on the order of tens of kilowatts. That's constant use all the time. Gee, all of a sudden, I'm not really so happy about it. Then when you throw in the overhead of all the other stuff, it gets really expensive to run. In fact, for a lot of hard drives, it's starting to be the case that it costs more to run them for 5 years than it does to buy them. So power is a bit of a concern here. Now, we also, as I said, want to make sure that we have technology that evolves over time. Storage. People are starting to say flash is great. Well, when flash gets cheaper than disk, we'll use it. We want to make sure that we don't have a problem that NASA already has, which is they have these old 7-track tapes lying around. Even if you could manage to unspool them, we don't have 7-track tape readers anymore, and these are mechanical devices. They're hard to build. Reading old tapes from a lot of the old NASA missions, not easy. We want to make sure we can read these. We also want to build a system that evolves. And the analogy I like to use for the way we build storage today is that it would be like building a house or you're building a new CITRIS building, right? Presumably, if the building lifespan if the building components last for about 20 years, it would be like saying 20 years from now, 20 years is up, knock the building down and build a new one. Now, I know some people might like that idea, but really, if you look at a building like the one we're in now, I don't know how old it is, but I'm going to guess on the order of 100 years. How many of the components in here were even imagined 100 years ago? You don't knock the thing down, right? You gradually go in and say, well, we need to have electric plugs. That electric plug, I will almost guarantee you, was not here when the building was built. That's why it's running in a chase outside the wall. But we found a way to graft it in afterwards. We found a way to make buildings evolve. Storage systems historically haven't evolved. You replace them by literally wheeling in a new system, copying the data from the old to the new. We don't like that. So what I'm going to talk about today is a system we developed called Pergamum. And before getting into the system itself, just a little bit of a history lesson. And we got this idea from Mary Baker. The name we got before, but she corrected us in the pronunciation. Mary got her PhD here about the same time I did, and also studied classics. So she knows about this stuff. So Pergamum was a library of the ancient world. In fact, it was the second largest library in the ancient world after Alexandria, located about over here. Pergamum was in what's now considered Turkey. And Pergamum is actually famous for a couple of things. The first one is that because Pergamum was built by a rival ruler to the Ptolemies in Egypt, the folks in Egypt wouldn't sell them papyrus, which really only grew in the Nile Delta. So they had to think of a new storage technology that would replace papyrus, and they came up with parchment. Pretty darn good idea. It's a lot more sturdy than papyrus. They had to manage the transition from papyrus documents to parchment documents. The second thing that Pergamum did that was relevant for what we are doing is that when they stored, instead of just taking things and throwing them in big piles onto the shelf, they actually built shelves that ensured things like airflow around documents to try and make the documents last longer. So they actually took steps to try and preserve the documents themselves instead of saying, big pile of them, we'll see what we can read in 100 years. So Pergamum, pretty neat place, and that's where we got the name for our archival storage system from. Plus the name Alexandria was already taken, so we couldn't use that one. Yeah, sometimes you have to deal with do what you can with what you got. Okay, so let's look at what we've got for archival storage today. Well, a couple of possibilities. You've got tape, and these are big tape silos that have lots of tapes. Robots move the tapes around, lots of drives. You've got disk arrays. In other words, go to NetApp, go to Sun, and buy a big bunch of disks. And then you've got a technology called MAID, massive array of idle disks. And this is already something that you can buy from people like Copan Systems. Now, we're going to rule out disk arrays right now because of one big problem: power usage. Disk arrays use an awful lot of power. Remember, power is bad. We don't want to use a lot of power. It's too expensive. So we're going to cross off disk arrays right now. Now, if you look at something like tape, notice that there are a couple of things that tape does very well on. It has low media costs because these tapes are on the order of $100 a terabyte. And power usage is very, very, very low because a tape sitting on a shelf uses actually no power. It just sits on the shelf. On the other hand, you've got lots of media per reader. In other words, you might have 60 tapes for every one tape drive, and you've got really bad random access performance. For those of you who are actually old enough to remember VCRs, you'll understand what that means. For something like MAID, your random access performance is not too bad. Your media per reader is 1. After all, the disk drive has a built-in reader, so that's pretty good. But power usage is a good deal higher because these guys use commodity CPUs that consume 100 watts each. They use commodity controllers, or special purpose ones, that consume 100 watts each. So for every 50 disk drives, you're paying 200 watts even if all the disk drives are turned off. That's 4 watts a drive, and you haven't done anything with it besides turning the disks off. Notice also that all of these have centralized controllers. This is another problem because it's a single point of failure. Okay? By the way, if people have questions, go ahead and ask in the middle because I'm a professor. I'm used to getting questions in the middle of stuff. So if you have questions, just kind of wave your hand and I'll see it and take a question. Okay? So they have all these disadvantages along with the advantages. What we wanted to do was build a system that had all the advantages of MAID and all the advantages of tape, and that's what Pergamum does. It has low media costs. It's got the same random access performance as MAID. It's got low power consumption, and it's only got 1 media per reader. So it's got all the advantages and hopefully none of the disadvantages that the other technologies have. Okay? So how do we do this? Well, what we do is we build a distributed network of intelligent disk-based devices. Now, I didn't bring one today, but you can actually buy the devices we prototyped on today at Fry's. How many of you guys have actually seen network-attached storage for the home? These little boxes that have a disk, a network connection on them, maybe a USB port? Show of hands. Maybe Buffalo makes them, D-Link makes them, okay? These things are a disk, a very low-power CPU, low power meaning under a watt, an Ethernet connection, and USB. We put flash in the USB, which we'll get to in a minute. But this means that a tome, and the reason we call these things tomes, by the way, does anyone here know what a tome is? Book. But what connotation does tome have? It's a book, but what connotation does it have? Large, heavy, old book, right? The first thing you do before you open a tome is you pick it up and you blow the dust off the cover, right? Okay? So a tome is smart enough, which is what we're calling our devices. They're smart enough to run independently. They run Linux. They have programs on them that do a lot of the internal maintenance themselves, okay? And they do things like managing redundancy internally. Fix the problem locally if you can. But if you put a bunch of these together, like a dozen or 100 or 1,000, they can actually use each other to provide additional reliability. And that's the goal that we have, is handle all the errors locally if you can. And if you can't, rely on your buddies to try and fix the data you've lost. Now, this controls 2 kinds of costs. The first one is static costs, the cost of buying the actual thing. Remember I said you could buy these things at Fry's? Well, if you could buy it at Fry's, that kind of indicates commodity, okay? Processors are commodity, disks are commodity, it's Ethernet and flash, they're all commodity stuff. Commodity translates to cheap. If you look at a lot of places that build their own hardware, that gets expensive, right? The second thing is that we have standardized interfaces, Ethernet. Ethernet changes very, very slowly. You can still buy connectors for ThinNet or even ThickNet, I suspect. Those things are 20, 25 years old. Okay, I'm willing to bet that in 20 years you'll be able to buy connectors for Gig E. I mean, it may be the case that they've been completely superseded, but you'll be able to buy them because there's an awful lot of wiring infrastructure that uses it. Commodity interfaces, again, means cheap. Also means it doesn't change quickly. Now, we control operational costs, the cost of running this thing, by using low-power hardware and by keeping the disk spun down. So how do we do that? Well, this box over here is what's inside a tone. So again, you have a disk, you have non-volatile memory. At the moment, we're using flash. A low-power CPU, again, about a watt. And by the way, anyone know how fast a CPU you can get for a watt? You get a 600 megahertz CPU that runs under 1 watt. Right? Probably a lot of you guys have them right now. Let's see. Because you've probably got one of these, right? This has, I believe it's 600, but it might be 500 megahertz ARM CPU in it. And obviously, this thing runs on a really small battery. And yes, the battery lifetime isn't great, but it's not bad either. That's a watt. So we have a network, low-power CPU, flash, and a disk. Okay? The disk is SATA, and the reason we use SATA is because it's cheap. Right? That's all we care about, cheap. Now, if you look at how the data is stored, we actually store the data, and we'll go into this in a little bit, in segments. So here we've got a region that has 5 segments, and the reason we divide things up into regions is because regions are what get replicated across disks, or actually erasure coded. And so you can see over here we have a region that has data, and it's got parity at the end. Now, the reason for doing parity at the end is very simple. If there turns out to be an error in here, we've got parity on the exact same disk that fixes it. Disks these days have literally billions of sectors on them. There are a lot of studies that show that, well, over time, those sectors go bad for any one of a number of reasons. If you want to know the details, that was some work done at NetApp and some other places, I can tell you, but they go bad. When they go bad, you want to have parity here so you don't have to bug the other disks in order to fix your own data. Right? So we'll talk about that, about how that helps reliability in a minute. Now, the NVRAM is really useful as well because in order to get to this disk, you've got to turn it on. 10 watts to turn this thing on, or 7 watts to turn it on, and leave it off, you're at 0, close to it. So we put a lot of information in non-volatile memory because flash is incredibly cheap to operate, 50 milliamps, as opposed to, which is about 0.25 watts, as opposed to the hard drive, which is on the order of 30 or 40 times that. So we put in this thing signatures. We'll talk about how we use those. We put timestamps. We put index information in there. Basically, we put everything in there you need to completely avoid turning on the disk unless you actually need the data on the disk. Disk stays off otherwise. And again, we have the network, which is Ethernet. And the reason is Ethernet is cheap, really cheap. Okay, remember, cheap counts. So how about power consumption here? That was one of our main goals. What's the power consumption look like? Well, power consumption here for a SATA hard drive is 7.5 watts if it's active. And by the way, for those of you who say, I'm not sure I believe these numbers, we actually get these off of vendors' websites. People like Western Digital are building green hard drives that only use 7.5 watts when they're on, and about 1/4 of a watt when it's off. Low-power CPU board, again, that's the whole board, including the network interface, 2 to 4 watts when it's on, under a quarter of a watt when it's not active, when it's in sleep mode. And NVRAM, hey, if you're not using it, it consumes no power. Even in very active use, when you're writing, it's under 0.5 watt. So that means when this thing is fully running, it actually consumes on the order of 11 or 12 watts. You can supply that level of power over Ethernet. There's already a standard for it. When this thing is not in use, well, you can do the math yourself. You're looking at under 3/4 of a watt. Really, really low power. Okay? A modern laptop processor, if you wanted to use one of those in your system, is 31 watts. That's about 4 of these things. So the point here is that we are very low power when we're not in use and low power when it is in use. So most of the time the disk is spun down, you're consuming on the order of 3/4 of a watt per terabyte. Remember what we said before? For something like MAID, it's on the order of 4 watts per terabyte if nothing's turned on. Now that saves you about a factor of 6. That's a pretty big deal. All right, so how about reliability? Because that's the second thing we have to worry about for archival storage. How do we ensure that our storage is reliable enough to last for, well, 40 or 50 years? Real simple. Let's look at a single disk. Right? That would be this guy right here. Notice that, as we showed before, you've got data blocks here and then a parity here. So if one of the data blocks here goes away, you can use parity to repair it. We've actually done experiments, which we'll get to in a little bit, that show you exactly how much parity you need. But if you have enough parity, you can simply ignore the effect of individual sectors failing, which is kind of a nice thing. But as we showed earlier, disks have this tendency to fail. So what happens when an entire tome fails? Well, we also do erasure coding across tomes. So if you look at this first redundancy group here, there's data here, and data here, and there's redundancy information. In this case, it's just parity in tome 2. So if tome 1 fails, you read tome 0, tome 2, and tome 3, rebuild tome 1, standard RAID. Again, one parity for 3 data, not enough. We've actually done experiments that show that you want to, let's say, have 13 data disks and 3 parity disks, read solid parity. The idea here is have enough parity so that you can look and check your data as infrequently as possible, again, to save energy. We'll talk about how well that works when we get to some of the experimental results. So how about reading and writing data? Well, reads are easy. You spin up the tome and serve the request. You're done. The good news about this is that if you want to read a bunch of stuff from one disk, sure, it takes 3 seconds to spin it up, but once it's spun up, it's a disk. I mean, remember, we were using off-the-shelf commodity disks. This thing is as fast as any other disk. You don't have to worry about seeking to new locations the way you would in a tape. That saves you a huge amount of space. Writes are a little more complicated. First thing you want to do is spin up the disk that you're writing to. If it's already spun up, you don't have to worry about this. You write to a new data block. Now, we designed the system to be optimized for no overwrite, because really archives, you very rarely overwrite data in place. You append to something, you write new data. Generally speaking, if you want to get rid of old data, it's because 7 years have passed and the SEC no longer cares about your files, but you don't tend to overwrite data in place. So we write to a new data block. Even if you were going to overwrite in place, we'll just garbage collect later. You then update the internal redundancy. Remember the redundancy over here. So you would update that redundancy first. Now it's protected against single disk failure. You then generate the deltas for the external redundancy. So if you update this disk, you figure out how this parity is going to change. You send the information over to it. Okay? There are 3 parity disks. You send it to all 3 of them. You then update the group's redundancy information when those disks are spun up. And you update the segment mapping, and the segment mapping is kept in flash, so again, you don't have to spin up the disk to use it. Okay? Now, as far as the protocol itself, protocol is very, very simple. There are only a few things you can do. You can read an object, write an object. You can also look for an object. Version 1 of the prototype used a custom protocol. Version 2, we decided to use HTTP. And again, the reason is long-term longevity, right? It's very likely that you'll be able to do put and get using publicly available tools for a very, very long time. After all, there are still tools for Gopher. I don't know who remembers Gopher. People are going, no, what's Gopher? Gopher was actually a protocol to actually get information from web servers before they actually had HTTP. Right? So before the web, people used Gopher. You can still get, I think actually Firefox still supports Gopher, which is, yeah, people are looking at me like, I mean, I don't know if anyone else provides Gopher, but I'm pretty sure Firefox supports it. So these protocols go away very, very slowly. If you use put and get, all you've got to do to read data is have a web browser or use wget or curl. I'm pretty sure that's going to be widely available, so standards. Now, when you want to choose a tome for new writes, you have 2 choices, and we try to be agnostic about how you do it. One way to do it is to pick a particular tome. I want to write here. Now, one reason you might want to do this is that maybe you're managing a bunch of photo archives for, let's say, thousands of people, and you say, this disk is going to be dedicated to the following 10 people. Whenever any one of them writes photos, they put it right there. That's a good reason. You might also say to Pergamum, hey, look, pick a tome. If you're a big company and want to store your data, you might not care where it goes. Just pick the best one that's already spun up, one that has the most space available, maybe one that has the least space available. All right? So you have a choice about either picking a particular tome or let the system do it. Okay. So how about consistency checking? One of the biggest things we have to worry about is how is this data going to last for hundreds of years, mean time to failure? We do a process called disk scrubbing, and this is something that we had developed a few years before this. But basically, we go through the disk and we read all the data and check to make sure it matches the parity, And we check, and then we record the signatures, and a signature is nothing more than a glorified version of a hash value or a CRC. It's a little bit more powerful than that, but we'll talk about it. We take the data, we record the signature, we check against the parity and make sure it matches. And then we record the signature in NVRAM. Now the first thing to notice is that we do have to scrub the entire disk on a regular basis, let's say once a year. We don't have to do it all at once. Because we're storing the signatures in NVRAM, we can scrub a gigabyte, record the signature, and then power it down and scrub another gigabyte 8 hours later. Or scrub 10 gigabytes today and repeat this every 2 or 3 days until we've scrubbed a whole terabyte disk in a year. We are recording the signatures in NVRAM. Those we can read without actually spinning up the disk. This approach has a couple of advantages. The first one is, one of the biggest things you worry about with a disk failing is when you turn it on, maybe it doesn't come on. This is a huge problem. If you're able to read 10 gigabytes off of it and have very few errors, you're pretty sure that most of the disk works okay. You may have a few sector errors, but that's all right. You're pretty sure that it's not the case that 99% of the disk is hosed, because that's not the way disks fail. So you turn them on every 3 days to make sure they're still working. This also makes sure that you can scrub the entire disk within a year, and because we have intra-disk parity, it is very unlikely that you'll be able to read a range of blocks, including the parity. We have numbers for how unlikely it is, and trust me, very unlikely. Now, of course, this is good for checking checking one disk. How do I know that this disk and these other 12 are all still associated properly? Well, that relies on what we call algebraic signatures. Again, very similar to a CRC. Let's say again you have n data blocks, and we XOR them, we get parity. If we take an algebraic signature like this, it turns out the algebraic signatures obey the same property as the data did. So in fact, you XOR them, you get the signature of the parity. What this means is that we can store the signature in flash and check if we only have the signatures that the underlying data is likely to still be correct. After all, if we didn't update it, it probably hasn't changed. We can check to make sure the signatures are still correct. So instead of having to power on all the disks at once, we just do this stuff all in flash. Problem is that segments are on the order of a few megabytes, and that means that there are going to be hundreds of thousands to 1 million segments on a disk. You don't want to have to exchange 1 million signatures to do the verification. So what do? Well, you build the equivalent of a Merkle tree. How many of you here know what a Merkle tree is? Ooh, that's scary. Yeah. Okay. So a Merkle tree is very commonly used in doing things with hashes like MD5 or SHA-1. The idea is, suppose you have this really big document and you want to generate one signature for the whole thing. Sure, you could take your 1 gigabyte and run it through a hash function, but that's kind of slow. What you might do instead is run, let's say, 4K through a hash function. Each 4K goes through. That generates a SHA-1 value. You have a SHA-1 here, SHA-1 here. You have a whole bunch of these. You've got 1 million of them. Now hash that. Now hash those in groups of hundreds. Now you've got 4,000 of them. Hash those, that gives you your one root value. So you build a tree. It's pretty easy to show that if there's an error anywhere in the tree, it'll show up in the root. We do the same thing, only with algebraic signatures. Again, the nice thing is that remember that these data blocks all XOR together to give you parity. Therefore, the signatures here all meet that same rule, and you can keep reducing the signatures this way. You now end up with one signature at the root of the tree. So instead of exchanging millions of signatures, you exchange one signature, which is really good. Because what happens is if I exchange one signature and it doesn't match, now I've got to figure out where the problem is. So what do? I go down one level. Well, if I go down one level, these signatures all match. That means the left-hand side of the tree here, that's not where the error is. The right-hand side of the tree doesn't match. The error must be on the right-hand side. Again, here I discover the left-hand side doesn't match. I would have to check the right-hand side to make sure it does match. We don't show that here. But since the left-hand side doesn't match, I now check one at a time. This one does match its data. This one does not match. There's a problem over here. Again, I would check the whole thing to see where the problem was. But notice that I can do this in log n time instead of in doing order n time. Huge difference, and it reduces the amount of information exchange, reduces the bandwidth. So again, I can check a lot more efficiently. Okay? So how do we rebuild lost data? Well, the naive approach is to spin up the entire redundancy group all at once. All 16 disks. Boy, that's expensive in terms of power. What we do instead is to rebuild lost data in an incremental way. Spin up the destination disk and then one of the source disks. copy data over. Spin up number 2 of the source disks, XOR it in. Number 3, XOR it in. It turns out that this is higher total energy consumption because you actually have to leave all the disks spun up for longer, but the peak energy consumption, which is what we care about more in a lot of cases, is lower. The reason we care about peak energy consumption is that affects things like how much power you have to deliver and how much cooling you have to have. Very big deal. All right, so how about reliability? well, we've done this stuff has all been done in simulation because if you look at the reliability numbers over here in hours, 10 to the 10th hours just for calibration here, they're about 10 to the 5th hours in a year. So this is on the order of 10 to the 5th years or 100,000 years. Now this is for a single group. So if you had 1,000 disks and your failure was up here at 10 to the 10th, that would mean you'd have on average one failure somewhere in your 1,000 disks in your 1,000 group system about every 100 years. All right? So remember, we had 2 kinds of reliability. One of them is interdisk reliability. So this says 15 plus 1 RAID, 14 plus 2, 13 plus 3. You could go to 12 plus 4. It would just mean a higher thing here. One of the things we found out, though, is that if you look over here, this says I have no parity at all on my disk, on the disk itself. Notice that the failure rate here is more than an order of magnitude worse than if you have 1 parity block for every 63. An order of magnitude worse, and it's actually 2 orders of magnitude worse than the ideal where individual blocks never fail. The point here is that if I keep 61 plus 3 at a cost of 5% overhead, and not very much performance difference, I get 2 orders of magnitude better performance, better reliability out of the whole system. So keeping 61 data blocks, 3 parity blocks on each disk gets me literally 2 orders of magnitude improvement, and as you can see here, matches the ideal case where no block failures ever occur almost perfectly. Okay? By the way, one other point to note here is that you see how these lines diverge as you move out to the right? The reason is that over here, your biggest problem is you lost 2 disks. Over here, your biggest problem is you lost n-1 disks and 1 or 2 sector failures. That means the effect of sector failures gets bigger as you move out to the right because, basically, with more reliability here, your problem is individual sectors failing, not entire disks failing. Okay? Okay, so we've addressed the reliability issue, we've addressed evolvability, we've addressed performance. Well, we haven't gotten to performance yet, but we need to worry about cost. Well, again, these are numbers for dollars. The problem is it's very hard to go to a company and say, we're a university trying to beat the crap out of your system. Could you please tell us how much it costs? It tends to be a very ineffective way of doing it, so we went and canvassed websites. Turns out that these are costs per 10 petabyte storage, and it turns out a Pergamum system is $4.7 million. That's a lot of money. But remember, this is for 10 petabytes, and these are slightly older numbers. The closest thing you can come to that is EMC Centera. All the other approaches, 3 times, 4 times more. It's also useful to look at operational costs. In other words, how much is your power going to cost at 20 cents a kilowatt hour? And that has to include cooling in that 20 cents. The answer is that you save about a factor of 5 over the next best one and over the cheap one over here. This is sort of cheap to buy, expensive to run. Right? So we're a lot better there. The other point about redundancy is that the reliability of Pergamum is much, much higher than any of these other ones. Okay? Because we have, as we showed before, mean time to data loss in a system with 10 petabytes would be 100 years. Nobody else can actually match that because they don't have the level of reliability in there. Now, those who have been paying attention will note that we are missing one thing on this. One thing here. We've got MAID, we've got optical disk, we've got regular disk, but we don't have tape. So we compared it to tape. Cost is comparable to tape. The operational cost is comparable to tape, but there are a couple of big advantages for Pergamum. First one, average access time, way faster, an order of magnitude faster, in fact. 1 media per reader. In other words, I can hand you a Pergamum tome and you can read it, just take it out of the system and read it if you want. Redundancy is a huge one. Yes, tape is pretty reliable, but it does fail. Tapes have been known to break and lose data all the time, and that system doesn't give you any reliability at all. People have tried redundancy in tape. Actually, Ann Chervenak, who was in grad school with me, tried redundancy in tape. It didn't work. So if you want to have redundancy for tape, what do? You make a second copy. Second copy will cost you at least $100 a terabyte because you've got to have a second cartridge. Well, guess what? That means this price goes way up. Okay, so you don't want to do that. Okay, so how about performance? Well, performance is actually okay. It's not great, but remember, that wasn't our goal. Our performance here is on the order of 3 to 10 megabytes per second, depending on what you're doing. Lower, it's lower than a tape. Tapes can run actually at 100 megabytes a second. but it's fast enough for archival storage. And because seeks are so darn cheap, you don't have to write everything out in a big stream, gigabyte at a time. You can write smaller stuff and it works just fine. Okay? Point here is if you had 1,000 tomes and spun up 1 in 20 of them, you could write 175 megs a second using our unoptimized prototype, and we're actually working on improving that number. So I want to talk very briefly about a couple of things we're working on now. First one is Logan. And Logan is an approach that actually lets you add devices to your library and have them automatically identified and automatically integrated. So we want to identify, number one, new devices you've added. Number two, devices that are kind of old and failed, which we actually already do. And number three, devices that you might want to replace because while it's not failed yet, this thing is only a 100 gig disk. It's taking up all this space. You can buy a terabyte disk instead. And that's what Logan does. It organizes tomes into hierarchical groups, which check to make sure data is working, and also says, by the way, you might want to replace this tome eventually. Okay, so that's ongoing work. I'm happy to answer questions about that during question and answer period, but because we're running short on time, I can't go into more detail on that. Second thing I want to talk briefly about is indexing the archive. And the reason this is a problem is that traditionally with archives, people have actually used large databases to index them. So you get a big SQL database in front of your archive and you ask questions about it. Now I actually talked to someone at Fermilab about how they make sure their database doesn't get corrupted, which is a really big problem. He said, well, we make backups every hour and then we do sanity checks on the backups of the index. And I'm thinking, that seems like a very bad idea because scalability is a huge concern. You make backups every hour and hope to God that it doesn't fail. This is not a good idea for keeping your system in one piece. So what we are trying to do is use the NVRAM on each disk to allow each tome to index itself and then be able to send out queries to only the tomes that might contain the information you want. And again, this is ongoing research. We actually have a PhD student who's hopefully going to finish up in the spring, and this is part of what he's working on. And the last thing, which in the interest of time I'll skip over, is how to increase archive reliability. And this is using something called wide stripe ECC. Again, if you have questions about this, feel free to ask. I'll be happy to answer them. But in the interest of time, I'll skip this. Assuming that'll let me skip it. Okay. Okay. So other things that we're doing right now, and this is just other research in archival storage, because we'd like to get more people interested in this stuff, include protection against rare failures, particularly geographically distributed, particularly geographic failures. Right? If you put an archive in Berkeley in this building, I hate to say it, but I know where the Hayward Fault is. I mean, look, I was in grad school here. Back when I was in grad school, the CS department was in Evans Hall. And remember that the big San Francisco quake, or actually Loma Prieta quake, occurred when I was a first-year grad student, or second year, excuse me. So when I was getting ready to graduate, I was on a regular basis, I had already gotten a job on the East Coast, I was copying my thesis data over from the West Coast to the East Coast every day. Because I was worried, like, if there's a big earthquake at the Hayward Fault, I'm screwed. I'll survive, but I mean, who knows about the data centers? So failure of an entire site is a big deal. One of the things that we've talked to people like the movie industry, right? We actually talked to some folks in the movie industry who want to use things like Pergamum 3 days after the big fire at the Universal lot. Believe me, they are very concerned about geographically guarding against failures. A second big issue that we aren't looking at right now, but it's a really big one, people like Raymond Lurie look at this, is how to preserve data context, not just the bits. We're preserving the bits, but can you read a JPEG in 20 years? Yeah, it's not that easy to read JPEGs, believe me. And we're also doing things like optimizing the implementation and leveraging the CPU of the client to try and do some of the work for us. Okay. With that, I want to try and thank a few people. First of all, the groups that sponsor the research, the Petascale Data Storage Institute, PDSI, and also the industry sponsors for the SSRC. And I also want to thank a bunch of people who actually have helped out with Pergamum. People like Kevin and Mark, Mark who is hopefully defending his thesis in a month, and Kevin, who did a lot of the reliability work. Colada Voroganti at NetApp, who helped us out with this stuff, and then also some other people, Professor Long, and 3 other students who've been working on this more recently. So with that, I'd be happy to take questions about the work that we've done.
Thank you. So we're going to use the microphone for questions so everyone else can hear.
Let's say the NVRAM fails.
Yep.
I assume you have to go through all the tomes to regenerate an NVRAM. How long does that take?
You don't have to go through all the tomes. Remember, there's NVRAM on each tome. So if a tome fails, right? Let's say the NVRAM fails, you simply toss the tome. You consider it to be failed. So you bring up a very good point that I didn't mention. Because a tome is a field replaceable unit, FRU, if any part of the tome fails, you don't try to diagnose why and replace that part. You simply say, the tome doesn't work, throw it in the trash and replace it. So if the NVRAM fails, you declare it failed and you replace it with a new tome. It then rebuilds that tome. If the disk fails, you throw out the disk. You throw out the whole thing and replace the disk part of it, as well as the NVRAM. So in other words, what we've done, instead of trying to diagnose why this one piece doesn't work, we say the tome is gone, put it in a new tome, and don't worry about it. Okay, so does that answer your question? Great.
So this obviously increases the system complexity, but have you looked into, since you're talking about powering things over Ethernet, actually just completely shutting off power to tomes?
Yes, we actually have. The problem with completely shutting off power to tomes is twofold. First of all, the problem is that we need to leave the power on a little bit so you can ask a tome, I'm looking for data, do you have it? Right? If you completely shut off the power, you don't get to do that. Now, you could, if you wanted to, if you knew you weren't going to be using a tome, no problem at all turning off power over Ethernet. You're absolutely right about that. But the advantage to having those lots and lots and lots of little 1-watt CPUs is very large. The cost of doing it is very low. Remember, if you have 1,000 tomes that consume 3/4 of a watt each in idle mode, that's 750 watts, or 3 desktop PCs. Right? So 3 desktop PCs and you've got a petabyte of data. Seems like a pretty good trade-off. You might want to leave them on. I agree with you. You can save a little bit by turning off power, but then you don't get to leverage all of the indexing and everything else you can get without turning on the disks themselves. So it's a good suggestion, but we think it's actually better to leave them on and just trickle power as opposed to turning them off completely. But you certainly could do that if you wanted.
Do we have any other questions here? Oh, okay.
What percentage of the disk are turned on and off at each time? Like, because we did some work about what is the optimal time to wait before shutting things off.
That's right.
And anticipation before turning them on, etc. Is there any work done on this in the context of your system, or?
So it's very workload dependent, as I'm sure you guys found out when you were doing the work. I mean, I actually did work in file migration back in, when I was a grad student 15 years ago. We haven't done any explicit work on that because it is entirely dependent on the workload. Our goal is to have only about 5% of the tomes turned on at any one time, and that tells you about what the access density is, right? Means that you can't be accessing, if someone wants to use this thing at 200 megabytes a second randomly spread, probably not a good choice. Of course, that's probably not a good choice for a tape system either, right? So what you really want to be using this for, as you said, is something where the amount of data being accessed is relatively small, and for writes, you just write to whatever tome happens to be turned on at the time. So we haven't looked at the question, but it's a very good question. This doesn't work for environments where you have huge numbers of random reads. It works a lot better if you have smaller numbers of random reads or larger batches of correlated reads. The example I'll use there is, again, the photo example. If you're browsing your photos from 3 years ago, chances are if you look at one of them, you're going to look at other ones too. Probably want to put them on the same tome. That way you spin up one tome, and instead of reading just the one photo you wanted, figure, yeah, you probably want other ones, we'll leave the tome on. Right? So looking at this stuff requires an archival workload, and unfortunately we don't have any good ones yet, although we are currently talking with Yahoo, and maybe if we're really, really lucky, they might let us look. But at the moment we don't have any good archival workloads, but if you have any, we'd be happy to work with you and try and use those. Yeah, behind you.
Yeah, when you talk to some of the folks in big data
Sorry,
centers,
you have to speak up a bit.
When you talk to some of the folks in big data centers, like in NERSC, for example, one of the problems is they wouldn't just simply make a switch from simply disk-based, from the tape-based system to a disk-based system. And the question is, if you have a multi-tier level, let's say going from online set of disk and then eventually to the disk and then eventually to tape, would you allow the Pergamum system to be used where a file system will be superimposed on the storage system itself?
Yeah, no, that's the whole idea, is you would want to put a file system on top of this. Remember that if it's accessed via HTTP, you can actually put a file system on top of HTTP. The goal here is to use this, though, to replace the tape part of things, not the what you're talking about is kind of the nearline storage, probably. The goal here is replacing the tape that you have at a place like NERSC or Livermore or Los Alamos, to replace the literally hundreds of thousands of tapes that you have sitting around, because it improves reliability simply because you can constantly check them, and apparently that's something people like doing. And also because it actually allows you to move things around, move data around without having physical things like robots in the way. You also get the advantage of not having to wheel in a new tape robot every 3 years when the tape technology changes. So our goal is to use this as kind of the lowest level of this, perhaps going up a bit and covering a bit of the nearline. Then you get your online storage a little bit larger, and hopefully instead of 3 levels, you have only 2 levels. Again, that's our hope, but if you want to use it in a different way, it'll work. It's just that you lose a lot of the power advantages if you actually want to keep most of the disks spun up at the same time. So you can use it that way, but probably not the best way to use it.
Okay, I think we're about out of time, and I'll just thank Professor Miller again for a great talk.
Great. Thank you.